Hi, I'm Terry Boult. I'll be giving you this talk for the second workshop on artificial intelligence anomalies and novelties. And the talk is on the difference between anomaly, novelty detection, and formal OpenSet open world algorithms. As part of that, we'll be referring a lot to our work on OpenSet open world. And a bunch of the references, I'm not going to put them on every slide because you can get our survey paper on surveying steps towards open world recognition in IJCAI21, and that'll give you all the references that I'll be talking about in our work. I'll have references if there's other people's work. So let's get into it, and I will give a quick overview of outline of the talk. I'm going to start with why I started researching OpenSet and open world, and actually as part of that I will start with anomaly detection and where that fit into my early research work and why we ended up moving to OpenSet. I'll get in a little bit about the difference between closed OpenSet and open world and the formalizations we go with and why we think those are important. I'll go through some formal OpenSet variations of classic SVM algorithms, and then I'll look at more recent algorithms for deep networks, including algorithms for open world recognition, and I'll end with some closing thoughts. It'll touch a little bit on metrics, but to keep this talk a little bit short, I know it was in the abstract, I'm going to cut out some of the work on metrics because you can find it in some of my talks from a CVPR workshop in open world vision. So I've been doing detection and tracking for over 25 years, and I've published lots of papers in that space. I was part of the DARPA VSAM program back in the 90s, and I've actually developed multiple commercially deployed systems, and a part of what will happen as I went through this process was learning from what I was doing in the lab to what's going on. So the DARPA VSAM program, part of what we did was working with some very complicated environments, and complicated environments might be things like this is an omnidirectional camera out in the field looking for snipers, and my commercially deployed systems included government work like that, but also ports and facilities like Port Canaveral, where we wanted to detect and track things both in the parking lots and in moving ships, or ships moving into a shore and what might be there. So as I started taking stuff out of my lab and into the real world, we quickly found the real world was very messy, and it also had some pretty high operational demands. As we went to commercialize our academic tracking work, we met with various clients, and the goals were to have less than 2 false alarms per day in their facility, because if it goes off too often, the security guards either don't trust it or just ignore it or just turn it off. So if we work through that, what does that mean in terms of our detection at a per frame level or per pixel region level? You can go through all the math, put together pixels on target, frames, seconds, hours, 100 cameras in a standard average facility we were looking at. And if we're allowed 2 false alarms per day, that means we can have 1 false detection for every 3 times 10 to the 12th windows. Turning that around, that means we need an exceedingly low false detection rate. So we had to take what we thought was pretty good at an academic level and ratchet up just a little bit to get there. So some of our research work had looked at like what we could do in terms of things. So here we see 6 temporal histograms. So every row in one of these images is showing you the brightness of, in this particular case, of a particular pixel, and a histogram of what that brightness was over a 30-second clip, and then that clip proceeds over a period of time. And so these are 6 different things. So a simple question, looking at these pixel histograms, which of these have targets in them? Which of these have anomalies? That is, their segments are different from their background. And which of these would you want to say, tell a security guard, you have to go look at this. So looking at that now, I'll put labels on them, and I'll tell you that only pixels A and B contain any kind of targets. So you might be looking at the swaying leaf in C and say, well, that's clearly an anomaly because you have this weird bifurcation going on. And what that really is a waving of a leaf in the sunlight. And so sometimes the leaf is facing you, sometimes it's not. F is shadows in a parking lot, so as the sun changes somewhere, it doesn't even have to be directly hitting here, it could be reflecting off a building. You get these complicated interactions of shadows. The walls of buildings have both shadowing and other lighting artifacts. Short grassy areas have a little bit of waving and a little bit of the breeze, so a whole kind of things going on. These little excursions here were actual people walking or cars going by. The shorter time ones are cars, the longer ones are people because they move slower. So this is the kind of stuff we'd already been looking at and trying to develop systems with. And one of the things we showed in our academic work was already that things really weren't Gaussians. When we first started this work, most of the people, and by far the most cited paper of the day, were people doing Gaussian mixtures as a formal model for anomaly detection to say when background pixels were or were not targets. In our work, we eventually were able to show more formally that it wasn't a Gaussian mixture. It's not even a stationary mixture. Distribution, so it can't really be just a simple Gaussian mixture. And even as a Gaussian mixture, you'd need a lot of items to be able to model it well, even if you made them temporally dependent. We ended up developing a much more efficient, all integer-based, dynamic, multi-background model with a bunch of updates to be able to handle all this stuff. And sort of, we published a bunch of papers at the academic level, and all of this was prior to trying to commercialize it. This is actually what got us interested in commercializing, is because our system was actually so good at what we were doing. We thought, oh, this will be commercially viable. And just after 9/11, a company was started, and they approached me about integrating this in, and we did that process. So, as I said, as I started that now, past academic stuff, those constraints came in, and they were a little scary, but as we went out and gathered real data in the potential customers' facilities or the customers' facilities, we had some difficulties to deal with. So we had to detect and make sure that we were detecting anomalies, but most of what we were detecting noise from a camera, moving branches, shadows, clouds, birds, bugs, animals, blowing trash bags, all of those things might be anomalies in some formal sense. They might be novel in some sense, but they're also false alarms. They're uninteresting. And in a complex world with complex features, representations, almost everything was unique in its own way, in some dimension of what we're looking at, and hence everything was either novel or not novel, or anomaly. And we had to really work hard. We did a good job at developing models for noise and shadows and clouds, which are a little bit more predictable, but birds, bugs, and bags were killing us. When a bug lands on your camera lens and crawls around, it produces patterns you have never seen before and are very hard to analyze. When bird dew lands on your lens, or birds just fly through the scene really fast, blowing trash bags present interesting things, especially in the water. So we had to work beyond just simple anomaly detection. And some of the system changes were straightforward. So if I start changing different parameters of our algorithm, we can do the standard ROC curves and look at what our false alarm probability versus misdetection. You'll notice these numbers are nowhere near the 10 to the 12th we needed to be. And in different data, the same exact sets of parameters would trade off. And so the best algorithm here is, maybe in this region might be the green, over here, might be the blue, right? And they all trade position, right? And so we had to move beyond simple, let's tune our system. We had to invent new classes of algorithms to go along with it, and we had already done some of that. We expanded on that. And with some other parameter settings using our quasi-connected component algorithms, we were able to get much better low false accept rates for things like noise and clouds and whatever, which were a little bit more modelable. But we really didn't, we had to do something completely different for nuisance novelty. And some of this stuff was really important. By nuisance novelty, I mean it is novel. We've never seen a bug land on our lens. We've never seen a bird fly like that. But we had to decide that wasn't a target of interest. So we had to be a little lot more careful in what we're defining. And just to give you a difference between what we got with anomaly, basic anomaly detection. So this is our early work in 1998 as part of the DARPA program, the academic side of what we're doing. And you're sort of seeing here, I'll play it again. This is the sniper detection problem, and there's a sniper out here in the grass. And these are the first little blips that maybe there's a sniper there. Here we're seeing much more consistent detection, and if I do things like temporal integration and fusing and voting, we can start to get pretty solid detections here at 15 feet. As we analyze this, by 2002 we were now working in the commercial version of the algorithm, and we're going to show you the detections. It's the same exact video, just reprocessed to sort of show the advances we made. So that's me being detected. There's some students behind the trees, which we thought they were hidden, but they weren't. And that box there is detecting the sniper. Now he's not even supposed to be moving yet. In the video, the way it was set up, I'm going to run upwards a little bit and then yell go, and then he's supposed to start moving. After we reprocessed this with a refined algorithm, we were able to go back and say, it called it Fort Benning, talk with the sniper, and found out that's when he said, yes, you really did detect it, because before you never mentioned that I went early. Now you know for sure I did. In that video, there was actually a little bit where we're sort of showing you the motion energy. Part of what's important for anomaly detection is not just saying that something's anomalous. Go back to that video. It's being able to sort of understand what's going on. So when we show you the motion energy in the video, I'll just skip over it. There are actually far larger anomalies going on here in the tree than there are where the sniper is. The sniper is barely visible. If you watch really carefully, maybe you'll be able to see him. So you have to analyze anomalies with respect to a much more sophisticated model than just what's normal for the region of the image or what's intensity. We have to look for intent in a sense to figure out what's going on and be able to ignore stuff. So in a second, you'll see these trees. That's all the motion energy. There's a ton of anomalies going on in the tree, and we have to learn to ignore most of those. So anomaly detection was neither sufficient nor, it turned out, was necessary. Not all the anomalies were interesting. In fact, most were not. And not all of the interesting security events were far from known examples. We actually had to deal with the fact that in parking lots, most people were speeding. Even though that was a security event, we eventually had to turn it off, post more signs. But it's not an anomaly that people are violating certain rules. And so both of those had to be dealt with in the way we have to deal with things. What was normal in a sense of anomaly from a probability point of view was very strongly dependent on what we decided to do with any probability and modeling assumptions. If we used mixtures of Gaussians, how many terms we added, how long the data was, how soon we initialized it. Had we ever seen this season before? A ton of things. They were always changing. They were not stationary distributions, causes lots of problems, and hence we just decided the entire approach was wrong. And then with our moderately high dimension, at least for the time of representations, we often lacked enough data to constrain many of the dimensions. That's why I said in some sense everything was always unique because we didn't have enough data to constrain everything. It was particularly difficult when we moved to bags of words representations because the varying numbers of densities made it very hard to talk about what the probabilities would even be. So in the end, we pretty much had to punt on traditional anomaly detection and move on to other classes of things. All positive examples are alike. Each negative example is negative in its own way, is a quote from a paper in CBPR 2001. We eventually figured out that all positive examples are different in their own way as well. And so we just moved on to something else. And at the time, that was my second company. We ended up selling it off, and I was going back to the academic lab, and I did another company a couple years later, and I realized it wasn't a one-off problem. We were dealing with multiple problems of visual recognition and biometrics. So in this case, we're looking at one of our animal recognition systems we did for the Air Force, where we're trying to recognize and distinguish endangered species, Mojave ground squirrels, from other animals. So we have to recognize a bunch of subclasses, and it's a pretty fine-grained problem. They're pretty deep, small animals, and we have to distinguish them. And then we also have to deal with all of the other standard things. So lizards that would walk through the scene, blowing brush, blowing bags, trash, burrs, all the same stuff we saw before. And I started thinking there's got to be a more way to approach this more formally rather than just ad hoc coding, which is what we did with the second company. So we went back and started looking at what does it mean for our problem. So a closed set problem, which is the way almost all machine learning at the time was being done, basically treats the world as a set of known classes, and everything is in one of those classes. So the classes form a closed set in the sense that the boundaries are closed, and the partitions of all of space. You choose any point, it'll tell you what class it's in. Now that becomes problematic if I think about taking my feature space and zooming out for a second and imagining what else is being labeled. And all my training data might be inside this small square, but I'm going to label everything. Right? So I'm not just labeling the stuff that was near my training data, I'm going to label this stuff. In fact, if these are linear classifiers, which drawn that way, right, they'll label everything. They'll label every pixel on Mars, Pluto, right? They don't care. They go on forever. They're infinite in space. So that's really not what we mean. I should have no business labeling things up here, let alone on Mars. And so we wanted to come back, and so we looked at this idea of OpenSet, which is combining the fact that we know that there are known classes, but they're now open sets. We don't know exactly where they end. We don't want to assume that there's a fixed boundary between them. And it's also not a partition of space. You don't want to label all of space. So we have to sort of balance this idea of open set risk. We want to find regions where we say, in here we're going to call it red, but not farther than that. In here is green. And the fact that over here we label it green with the closed set is bad. We want to just label it unknown. And so open set recognition can be viewed as a combination of multi-class recognition and novelty detection, or multi-class recognition and anomaly detection. But importantly, we have to balance different types of errors, and we have to consider the risks of black swans. What are the risks of these novelties? And I'll come back to that and we formalize that in a second. And then we were also looking at and wanted to get to what we call open world recognition. In fact, when I first defined the term open set, a couple of people were like, well, why didn't you just call this open world? It's the open world. It's like, no. In the open set, I never learn these new things. In the open world, I have to detect new things and learn about them. Okay? And it's not, as some other people have talked about, oh, the open world doesn't have to have long tails. I can have an open world with small tails because, for example, a new model of car comes out every year. Right? There's a fixed number, but there's actually lots of them, so it's not a particularly long tail kind of problem. I have to decide that this region of space I've never seen anything in is open. And then if I start seeing things down here, I can define a new gold class and now understand what's going on. We'll come back to that as we go through the formalizations. So in our first paper where we formalized this, importantly, we broke our goal up into two parts. We're going to define open set risk, which I'll do for you more formally in just a second, and empirical risk. Empirical risk is what we normally minimize. Right? This is the sort of training error, expected loss on the problem. And we're going to take this, and it's important that we're going to have some balance, which is up to the end user design, which is a regularization constant to balance open space risk and empirical risk. So what do I mean by open space risk? So if I think of all of my labeled data, I can draw some boundary. I can say if you're farther than this away, and like any anomaly detection system, that involves some model of things. Some things might be less clear. Is this question mark far away or not? but these are pretty clear. We're not actually answering the question, how do you define the measure of what does it mean to be far? That's domain specific, we'll leave that up to the user. But the idea of open space risk then is to look at what am I labeling. So I'm going to define an indicator function f that is 1 if I've recognized it as one of my known classes, and 0 if it's not from one of those known classes, if I say it's not from one of those known classes. And then I'm going to define my open space risk as this ratio of the integral of that function over all of open space and divided by the integral over some ball that includes all of my training data. We'll call that S sub 0. And for lots of problems, open space depends on my representation, but if my representation is a bunch of floats, if I have an n-dimensional vector of floats, then my open space is all of r to the n. It's infinitely large, and it includes Mars and Pluto, and so I have to worry about how much I want a label of that. And part of the goal here in terms of balancing these two was motivated by looking at SVM theory at the time and Vapnik's trade-off spaces, where we know that if we increase the capacity term, right, we're going to get, if the capacity is too small, I get underfitting. If I get too much capacity, I start overfitting, and this is true in general for machine learning. And this idea led in SVM space to what's called max margin, and we wanted to have something similar where we're looking at balancing the open space risk and the empirical risk. And it's important that open space risk is not something I can necessarily sample. Here I have a set of knowns and validation data that I can sample over, but open space is an unknown space, and so I don't know the frequency of things, I don't know where they are. And one of the things that's really important when I deal with this is that there's been lots of other work, which is called classifiers for rejections, anomaly detection. There's a whole bunch of stuff in that space where basically I have a classifier that can say this is not my class. And there's a whole range of those, and it's also called out-of-distribution detection algorithms. And there's a whole bunch of these things that are not OpenSet algorithms because they do not bound open space risk. So, for example, if I take three linear classifiers and I say anything that's near the boundary I'm going to say is unknown, and then everything that's far enough away, like I would in SVM, those are known, this is going to have unbounded amounts of open space labeled. Right? So this goes back to the very old. So, and the problem with that is if I have unlabeled open space, then if r sub 0 here is infinite, then all answers, because this is infinity, the argmin over the space of functions of infinity plus whatever is still infinity, and so all functions are equally bad because they all have effectively infinite mixed open set error. And so we want to make sure that this is at least bounded. The optimization after that gets a lot more complicated, but it's not hard very often to answer, is it bounded or not? And if it's not bounded, then you know you have a problem. And so if you don't bound open space risk, you're definitely going to have a problem. And so almost all linear classifiers, which are still extremely widely used, end up with infinite open space risk because they label everything and things go on forever. And a number of people want to say, well, you know, if I assume things like all things are equally likely, in the space of functions in unbounded infinite spaces, there are no uniform measures. I can't say things are equally likely. It has to be lumpy, and so I'd have to play some very specialized games to make that work out. And it's really, you might be able to do it, but it would be really complicated. So how do we get there? How do we get these OpenSet algorithms? So most of the ones we've looked at are really based on the idea of either kernel machines or density models, and it comes down to this generalization of sort of thresholding Gaussians, which is a long time thing people have been doing. And although I'm not a big fan of doing it with Gaussians, the basic idea is simple. If I take something like a Gaussian that has a maximum value and then decreases monotonically away from that, as I get farther and farther away, my probability gets smaller and smaller, and therefore at some distance I can threshold, and I will get a compact space, a compact set, that I can then say inside of this I'm going to say is known and outside is unknown. And so I can do that with multiple classes and then use that thresholding process to get there. Now, this is not actually completely new, although we formalized it with respect to OpenSet. The idea has existed for much longer. And in fact, the idea of using one class classifiers, which part of what we actually ended up using in my company, comes around to some of that because you want to be able to say it's known or unknown, and the one class is known and everything else is unknown, and so you hope to do that. The problem is if I start trying to use multi-class problems with one-class classifiers, I run into problems. So this pink area here is a one-class classifier using just the ones out of this data set. And you'll notice that while it's able to reject the unknowns, it also unfortunately includes all of the twos in there. And if I start moving on to a radial basis function binary SVM, So I still am using Gaussians, but now I'm using combinations of them. I end up getting this surface here, which corresponds to the blue surface here. And so this is the RBF binary SVM for class 1. It's got a good job of keeping all the 1s, rejecting all the 2s, but it actually includes all the unknowns. The fact that it's decaying isn't enough because it has negatives, and you add them together, you get a more complicated function. So we struggle with this, and I'll come back to SVMs in just a little bit. But one of the things as we were going through this, right, we came upon a critical insight that came from some of our work in biometrics, which is that what really matters the most is that in this kind of problem is either the most distant positive, the most far away thing I've seen from my class, excuse me, or the nearest negatives, the nearest novelties, the nearest anomalies, right? And either of those, the most distant positive or the nearest negative, is what is formally called an extreme value problem of the first type, if we're going to use it more formally. And to be honest, this is true of most machine learning. In most cases in machine learning, or what you might call AI at this conference, what we really care about happens at the boundaries. It's not what happens in the middle of the class. It's always the boundaries between two things that make the difference. So it's the most extreme of this approaching the most extreme of that. And that's all about extreme value theory, right? And there's a formal process because it's bounded from below that says it's going to be a viable as an approximate for the extreme values. And there's a whole bunch of stuff that goes with it. So if you take away nothing else from my talk today, remember this. Go out and learn a little bit about extreme value theory and how you might use that with respect to anomalies and novelty. But I will tell you, as I try to highlight from our early examples and my own experience, right, just being an outlier from extreme value theory from an anomaly point of view is not enough. But this might help you formalize some of where you're going and can be helpful. So basically, to sort of highlight that idea, we really have two kinds of fitting we can do. So if I have my pluses and minuses, the positive and known classes, so this is class 3, everything else, classes 0, 1, and 2 are unknown. I can think about how far am I from the SVM decision boundary, that sort of bumpy surface I showed, and I can say, okay, I can then do one of two things. I can look at the most extreme green scores going this way, what's the most extreme positives, and that is the probability of inclusion of being from class 3. Or I could look at, I don't want to be coming from class 0, 1, or 2. I don't want from the negatives, and we call that the probability of exclusion. And then we actually built algorithms that sort of combine this. So using just the probability of inclusion, we call that a PI-SVM. We can take the same example I showed you before, and now I can fit what is effectively a binary SVM. I take this surface, and then I do this extreme value calculation stuff on it, and I get something that looks like this, and I'm able to get this nice green region that says this is class 1. It's now able to reject a lot of stuff. It doesn't include any of class 2. It is a little asymmetric because it's got a sharper boundary between 1 and 2 because it had examples it has to avoid. The backside is a little softer, but it's able to do a pretty good job. We defined another one called the W-SVM, which includes probability of inclusion and exclusion. You can read more about those in some of our papers. But we were still also interested in terms of a formal open set. When is an SVM working? Because sometimes they seem to work and sometimes they don't. We'd already seen that in our own research. So we did a bunch of research in terms of what does it mean formally for an RBF SVM to be a CAP model, for it to have the properties we need for open set classification. And so it turns out that with a bit of effort you can prove, and we recently published a paper, although we submitted it a long time ago, it's gone through multiple iterations, that an SVM with an RBF kernel has bounded positively labeled open space, so it has finite open space risk, if and only if the bias term is negative in this formulation, and if you use the formulations where you use minus the bias term, then it would be flipped around. But basically, this term, if they're a mixture of RBFs that are going to 0, which is classic for all the RBFs you have to have, this term can go to 0, and so it becomes dominated by what happens with this. And so you sort of run out on that surface, and in the example I showed you before with the binary SVM, it had a positive B, so it sort of thresholded towards 0. And then we looked at a bunch of problems, and in the paper we went through a bunch of these, and we looked at bunch of different data sets, fit a bunch of different 1 versus all and 1 versus 1 SVMs, and there's lots of different arguments about which ones to use, and looked at what fraction of them were had the negative bias, so that they're actually formally open set. And you'll see for a whole bunch of problems, you can get a lot of them that have, if in 1 versus all, a lot of them are open set because they have formula, but not all. And then if I look at the 1 versus 1, very few of them, about half of them were. And so sometimes you get lucky, sometimes you don't. But with a little bit of things, and in our paper we show a way to guarantee that your SVM always has that positive process, or it fails and says it can't find one. So But that was all SVM land, which was an important part of the earlier parts of the century. But as deep networks came around, we realized we had to move forward and move to deep networks. So in our 2016 CVPR paper, we looked at how do we make this work for deep networks. So this was our first cut at this, and our basic idea was to take either the feature vector or the logits. Either one of us can work. We actually found for this problem it was better with logits, but the paper looks at both. And we take a bunch of the deep features, average them, and compute what we call a mean activation vector. And then for everyone else, we can look at how far are those from the mean activation vector. And because that's a set of distance functions, we care mostly not about what's happening near the mean, which might be multi-lumpy, especially for something like this. Baseball class has got balls, and then it's got baseball fielders. These are very far apart in some sense, but they're all baseballs. But towards the tails, we can look at what are the most extreme of these. What is the frequency and the number of times things are very far away? That fits our CAP model by fitting an EVT with Vibbles, and we get that. And for a bunch of people, that EVT fitting is what OpenMax is. OpenMax in our paper is actually a little bit more complicated because we do that EVT fitting for lots of different classes, and then we use that to adjust the probabilities. So we take what used to be a K way output of softmax, we make a K plus 1 that's adjusting it based on what's going on. And that allowed us to get some pretty interesting results. So we take our baseball classes or mean activation vector. I can take a real image and I can sort of see it's different in lots of places, but it's still got things going on. And overall, OpenMax says it's still baseball. In fact, it had the same score as softmax. It didn't really decide this was unknown. If I take a fooling image, which was some of the earlier work towards adversarial, this looks very different. But the softmax score for this is 100%. It's a baseball. OpenMax says no, it's not at all a baseball. It's 95% sure it's unknown. It might have also been a tablecloth. OpenSet images. So this is an image that is either potatoes or rocks. I'm not sure which. Softmax says it's 15. It's the highest score is baseball. OpenMax says 0.17 for it being a baseball, but its biggest class, 80%, is unknown. So it's pretty sure it's unknown. And so this was actually pretty interesting for the time, and it allowed us to do good things. But really, having your class represented by a single point in the middle is pretty weak. So we then moved forward with our work and developed this thing called the extreme value machine, which came out, and it's easy to install. Like you can literally pip install it. And it uses our margin distribution theorem that's really derived from EVT to sort of say, instead of saying I'm going to have an RBF kernel, because at the time it was one of the things we'd seen works pretty well, we're using these Vibbles, and the Vibbles are fit to the data. And importantly, we designed this so that it could be easily updated. We did a bunch of papers on incremental SVMs, but they're really expensive and hard to do. So here we can sort of view this as Vibble probabilities with a particular extreme vector, like a prototype, and then just sort of adjust it by adding new extreme vectors and adding probabilities. So I could take the original point. If I start seeing some new classes, I can update that, which does two things. It shrinks the existing class A to stay away from this, and then it adds a new class for the new pluses and can add. Right? So this is a straightforward way, and this allows us to do a better job on open world learning. And open world learning is where I have to decide that I detect something as unknown, get the data labeled somehow, and then do incremental learning to do this. In our first paper in 2015, we actually didn't actually do it quite that way because we didn't detect the things as unknown. We measured its OpenSet performance, but we also labeled all the data, not just the ones that were unknown, and then use it forward. So I'll come back to that. That causes a problem in the way the protocols were done. So, but in proper OpenSet worlding, we should either label the data, or maybe we could cluster to label the data, and we'll come back to that as we go through this, right? So this allows us to look at sort of the problem of closed set, open set, and open world. So in closed set, we're running along. We have different feature sets allow us to get different levels of performance. And so here what we have are just standard supervised features. So if it's at S, it's a supervised feature. If it's an I, it was using self-supervised features from ImageNet, and P is self-supervised with places, and then I can have with labels or without labels. And so we're going to do different kinds of learning. And one of the things to see is when we go from closed set to open set, of course, there's a huge drop in performance. There's a whole bunch more classes. This is actually using 1,000 ImageNet classes and 166 unknown classes, which are the unlabeled novelties you want to detect, and about 10% novel data. So there's a big drop because now I have a whole bunch more classes, and they're messing up my performance. But for OpenSet, you just continue that way, right? So you're a little bit robust. You drop performance, but you just stay at that level. The important thing about open world is to detect that those things are unknown, and in this case, we really are detecting they are unknown and then getting them labeled in the first three cases, And in the other cases, we're not even getting labels. We're just doing it without any labeling, and so we're just doing learning without labels, which makes this much more interesting. That last part, instead of getting labeled data, we just cluster, and we use cluster IDs to sort of drive stuff. So interestingly from this, one of the things we found is that using self-supervised features really help. So here's what happens when I do open world learning with fully supervised features where I get a label for everything I said was unknown. If I use just supervised features and I get no labels, that's the red curve. It's okay, but not as good. If I use self-supervised features plus supervised features, I get a richer feature space, and I'm able to outperform without any labels during the open world learning. So just doing the clustering, I'm able to outperform the supervised features. And that to me is very interesting. It says there's something really nice going on here that we need to explore a little bit more. So we started to do this just to give you some examples. So in this case, we were learning from some ImageNet classes, and we had some held out classes, and we were able to do a pretty good job of learning these possible classes, right? So this looks like sort of tree tops. This looks like tree trunks. This is sort of feather-like leaves, yellow leaves or yellow flowers off the trees, right? So all of this is sort of interesting. I will say that there's still some ongoing work here because what we want to learn with labels has got to be measured properly. So that brings us to the last little comments in the talk, which is what do we want to measure or what not to measure? So first, I'm going to point out that if we're dealing with open world learning or OpenSet learning, we have to somehow simulate unknowns and unknown fractions of unknowns and measure the impact. And we have to be very careful about this because if we use too much knowledge or we give everyone all the data, then it's really easy for the graduate to fall into what we call graduate student descent, which is optimizing indirectly on the test set. You have the test set, you run an experiment, and then you iterate until you get better and better performance on the test set. But what you've really done is you've indirectly tuned parameters using the test set, which is inappropriate from a machine learning point of view. It's actually good to have some held out sets. So things like the original ImageNet held out their test set, and everyone now just tests on validation data. And in the Sail On project that I'm part of, right, the TA1s have data we don't get to know what their labels are. And so we have to be honest about this, which makes it more challenging, but it's also really important if you really want to advance the science to make sure you're not indirectly cheating on what's going on. In open world, especially, we have to deal with the detection and the fact that detection errors cascade into learning errors, which cause you more problems. And our early papers failed to do that. We labeled everything, and that causes us lots of problems in terms of looking where the predictions are. So we have to be careful to make sure we're modeling the real thing. And so this, however, makes experiments extremely tedious because every time I change one detection error, I've got to rerun all the detections after that because I've changed things. It's expensive. And then finally, when I'm looking at what I want to measure, system design choices and hence evaluation metrics depend on the costs and risks of different errors. So, what's the error for a wrong label for any particular known class or for every known class? Are they equal or some more important than others? What's the labeling error for an unknown? Is there a particular label or missing it, right? So all of these are classic problems. In open world learning, I have to be particularly careful because I have to look at the different mixtures of how many unknowns do I have versus known unknowns versus the ground truth label, and what am I supposed to get, the ground truth label or just good clusters? And then the range of fractions of unknowns that may occur. Am I expecting to get 10% unknowns or 20% unknowns or 50%? All of those change what it is I'm looking at. It's a very complicated space, and if I'm doing this for a real problem, I go to the problem and it helps me answer those things. But I don't know what the real problem is here. We're dealing with academic studies, and so we have to be careful. There's a bunch of measures that have come out since our first papers where we use mostly F1 measure and accuracy, which are still widely used. They're not perfect. There's a lot of things. We've got a bunch of other papers that have looked at measures since then. But the important thing is we would design our algorithms differently for different goals. And you really don't want to mix goals. And so you want to be very careful how you look at that. As Albert Einstein said, everything should be made as simple as possible, but no simpler. Okay? For OpenSet, open world problems, metrics and data sets need to reflect the underlying problem. 30 ablations on a toy problem don't tell me near as much as one test on a large, meaningful data set. I've seen tons of papers with CFAR10, and I could care less for almost all of them because CFAR10 is not my real problem. If it's your real problem, enjoy. But I've been looking at things that are a little bit larger and more complicated, right? Most of us are just building tools, so there's no way for us to tie the problem, to tie our evaluation to the problem, to the underlying problem. And therefore, we can't really justify simplifying better to a single number. High true positives are a very different place of the curve than low false positives, and I might need two very different designs to get there. I shouldn't just try and mix them together. And so along that lines, anytime you see a paper that is using area under and some curve, ROC, PR, whatever, AU, OpenSet research group, if it's saying AU, it's basically saying I'm going to combine a bunch of stuff, equally weighting them, and in my view, it should be read as academically useless, XYZ. Just don't do it, right? You can simplify it, but no simpler than it needs to be, and we don't know exactly what we want to measure. So report curves and plots and much more detailed data, and don't try and tell us that you're better than someone. Show us where you're better, where you're not, and make it a more meaningful thing. So with that, I will take questions. You can find most of the code for our work at OpenSet on github.com/fastlab, and references to our work can be found in our AAAI paper that I already mentioned. And I'll leave this up on the screen while I take questions.